Alright, thanks for watching, and today I want to solve an analysis question that actually sounds harder than it actually is. And that question is also, by the way, a very famous question on the Berkeley prelim, in case you're interested about prelim questions. And the question is as follows. Suppose Sn is a sequence Sn is a sequence with the property that every subsequence has a further subsequence. I know, yo dog. So has a further subsequence that converges to S. So let me just illustrate. So what do we have? We have this sequence Sn. So think of it as a train. And we know that every express train, so every subsequence of Sn, so think of Snk, has a further subsequence, so a sub-subsequence, like an express train. Think Snkl that converges to S. And it turns out, so if every express train has an express train that gives you to a destination, it turns out that the train itself converges to that destination. So show that the original sequence converges. Converges to S. And as I said, it's a problem that where the statement is much harder than the solution, so I was very confused about this as well. But let's just do it by contradiction. So what do we have to show? So prove by contradiction. Suppose Sn doesn't converge to S, and essentially what we want to show, we want to find one subsequence with no convergent subsequence to S. Okay, so find an express train whose express train doesn't really converge to that destination. So, but how do we do this? So what does it mean for Sn not to converge to S? This means there is an epsilon such that no matter what threshold I give you, for all capital N, there is an N with Sn and S not being close. So again, picture-wise, what this says is there's a very specific error such that no matter how big your threshold, I can think of this as S, there's always one value of this sequence that's outside the good region. So no matter which N I give you, you can always find at least one element of this sequence that goes outside this region. But here's the thing. So, again, N bigger than capital N. Now, the thing is, this holds for all N. So let's start with, let's say, 0. Okay? So what do we know? So with capital N equals 0, we know there is N1 such that Sn1 minus S is bigger than epsilon. So it's a very beautiful construction actually. So again, with your threshold just being 0, we know there's at least one value of the sequence, let's call it Sn1, which is outside the good region. But now here's the thing, let your new threshold be n1. But now with capital N being n1, we know there's another value after n1 that is outside of the good region. So there is n2 bigger than n1 with Sn2 minus S bigger than epsilon. So it might be here. But then you can continue. Let n2 be your new threshold. And then you find there's Sn3 that's outside your threshold, etc., etc. And generally, you find Snk be outside your threshold. So in that way, we constructed a subsequence, you see a subset, if you want, of Sn, that's always outside that region. So in that way, we construct the subsequence Snk such that for all k, Snk minus S is bigger than epsilon. And now here's the thing. Well, of course, Snk doesn't converge to S because it's not inside the good region. But more generally, notice no subsequence of Snk can possibly converge to S. Because you see, all the values are outside the region. So there's no way that some of the values could be inside, even if you take a subsequence. And therefore, notice that no subsequence of Snk converges to S. To S. And which, if you want, contradicts the fact that every subsequence of Sn has a convergent subsequence that goes to S. You see, it kind of contradicts our assumption that every subsequence of Sn has a further subsequence that converges to S. Right? How nice is that? And again, I think the statement is very complicated to understand, but the proof hopefully is more manageable. But the cool thing is, with the same construction, we can actually solve another problem that I also found, and it's the following. Suppose Sn is a sequence, it's a bounded sequence, so that's very important. With the property that every convergent subsequence, so it's very important that it's convergent, subsequence converges to S and show that Sn, the whole sequence, actually converges to S. So in other words, suppose Sn is a sequence with the property that every convergent express train goes to a specific destination S, show that the whole sequence goes to S. Now, first of all, the fact that it's bounded is very important, and in fact, here's a counterexample. So consider Sn to be, I think, 0 if n is odd, and then n if n is even. So what does it look like? It starts at 0, and then, because 1 is odd, and then it goes to 2, and then it goes to 0, and then it goes to 4, it goes to 0, 6, etc., etc. So it just bounces back and forth. Kind of like stonks, if you like. Now, here's the thing. What does a convergent subsequence look like? Well, the only way this can converge if it's eventually 0. You see? And therefore, every convergent subsequence must be eventually 0, and therefore it must converge to 0. But the question is, does the sequence itself converge to 0? No, it just diverges, because it bounces back and forth between 0 and infinity, in some sense. Alright, and let's prove this, and we will prove this by contraposition, which means, suppose Sn doesn't go to S, then find one convergent subsequence that doesn't converge to S. So again, just to clarify, so suppose Sn doesn't go to S, and then show, there is a convergent subsequence that doesn't go to S as well. And here's a cool thing. The same construction that we did before also works here. Well, almost. Because remember, that was the good region here that's close to S, where we want our sequence to be. But then what we did, we constructed a subsequence of Sn, called Snk, that is never in that good region. So let Snk be as before. The only issue is, so you would think Snk, that's the solution to our problem, because yes, it doesn't converge to S. The only issue is, this Snk isn't necessarily convergent. However, remember we assumed our sequence was bounded. So there is one theorem that tells you something good about bounded sequences. Well, it's the bolzano-weierstrass theorem, which tells us that every bounded sequence has a convergent subsequence. So, since, well, the subsequence is bounded because the original sequence is bounded, since Sn is by, again, the bolzano-weierstrass, and let me write this very fancy German, okay, so scharfes S, theorem there is a convergent subsequence in SNKL, okay, that goes to let's say S prime. Not necessarily S, in fact, it cannot go to S. That's the whole point. So again, we have a subsequence SNK, and what we did, we found a convergent subsequence SNKL, kind of like this. But then the whole point is, okay, first of all, SNKL, well, it is a subsequence of Sn. It's just a subsequence of a subsequence, which is still a subsequence. However, SNKL, well, it cannot converge to S because it's always outside the region. So then, SNKL, if you want, is a bounded sequence. It's a bounded subsequence of Sn. I think, so not quite bounded. So SNKL is basically a convergent subsequence of Sn, but the point is SNKL doesn't go to S by construction. It's always outside the good region. And then we're done. All right, thank you very much.